Okay, today we're going to be looking at 4.1 notes, starting talking about linear functions. And so the definition here says a linear function is a function defined by an equation of the form f of x equals ax plus b, which you're used to seeing. In the past, we always used to call this mx, right, which was your slope and your y-intercept. We know all of this, where a and b are constants. The graph f of x equals ax plus b is a straight line, obviously. So suppose we have a linear function. Again, this is just defining a linear pair. The input is 1, the output is 0, the input is 2, the output is 3. So we can write those as ordered pairs. And so now that we have ordered pairs, we can obviously find our equation. We'll first find our slope, x2 minus x1. y2 minus y1 over x2 minus x1. And so our slope is just 3. And then we can use point slope form, y minus y1 equals m times x minus x1, and we can work this out, and our equation is just y equals 3x minus 3. Or f of x, if we want to use function notation, which would be more proper, f of x equals 3x minus 3. Okay, very easy review question. You guys all know how to do that. Example 2. We're going to put this same type of question now into a word problem. So we have a factory owner who buys a new machine for $8,000. After 10 years, the machine has a salvage value of $500. Let's write ordered pairs, just like we did for that first one. We can write ordered pairs. At time 0, the cost is $8,000. At time 10, the machine is now only worth $500. So we can rewrite them as ordered pairs, and now we can find the formula. So again, let's start with our slope, y2 minus y1 over x2 minus x1. And so our slope is negative 750. And then we can just, this is obviously our y-intercept, 8,000. So our value function, v of t, would equal negative 750 t plus 8,000. Use the depreciation function determined in part A to find the value of the machine after 7 years. So all that I'm going to do is plug in a 7 for time. And after you work that out on your calculator, you should get that the value after 7 years is about 2750. Now that would make sense that it's obviously less than 8,000, but still more than 500 because that's what it was at 10 years. Okay? In the study of economics, a function that gives, the cost c of x for producing x units of a commodity is called a cost function. We define marginal costs as the additional cost to produce one more unit. Okay? All that marginal cost really is the slope. How much does it cost to produce one more unit would just be at slope. Okay, so our slope is our change in y, change in x, and in this case it's considered the marginal cost when we're dealing with an economics problem. So here's our cost function for producing x bicycles. C of x equals 625 plus 45t. So where's that slope right there? There's my slope, 45x. So there's the slope, 45. So find the cost of producing 10 bicycles. Well, we just plug in a 10. Nice and easy. And it would cost us, after I work that out, $10.75. Okay. What's the marginal cost? Again, that's just the slope. And so my slope would just be 45. All that it means is it's $45 to produce one more bicycle. Use the answers in parts A and B to find the cost of producing 11 bicycles. Well, if it costs $10.75 to produce 10, I would add the 45 to produce one more. So it should be $10.75 plus the 45, and I should get the cost for 11 to be $11.20. Now I can check it by actually evaluating C of 11. So let's go to our original function. And if I actually plug in an 11 and work that out, sure enough, 625 plus 45 times 11 also equals 1120. So it does work out. So you could do either way. You could either just add the 45s each time, or you could just plug in the 11 and it would work. Okay, next page. We're going to talk about using a regression line on your calculator. Okay, so you guys have all done this before. There's two different situations when you would have to use a regression line. If you're given x and you're trying to solve for y, these are the steps you would use here on the left. If you're given y and you're trying to solve for the x, then you would use the steps on the right. So let's go through example 4. The regression line given by the equation f of x equals negative 0.370x plus 962.041 is based on records from 1911 through 1954 for the evolution of the record for the mile run. Use this regression line to estimate what the world record for the mile run might have been in 1999. Okay, so what do we want to do? We just want to use that equation, right, and that's our regression line. We want to take that 1999 and we want to plug it in, right? So this is my x value. So I'm just going to take that and I'm going to plug it in there, right? And so when I plug that in, f of x, right, times 1999 plus 962.041. And again, this is just using our regression. We just type that in the calculator. And you get f of 1999 is 222.411. And so this would be the seconds, this is in seconds, for that mile run, which is how many minutes? Well, 222, divide that by 60, so that's 3 minutes. Which would be 3 minutes and 42.411 seconds. So the world record in 1999 might have been, according to this regression, 3 minutes and 42.411 seconds. Okay. Check the prediction against the actual record of 3 minutes 43 seconds, 0.13, set by, I'm not going to try and pronounce that name, of Morocco. Compute the percentage error. Okay. Oh, let's go back up to the table at the top. Sorry, I forgot this. The other way to do this, so you could just plug this in your calculator, which is what I just did. The other way would be to use the regression line. And the way we would do that, right, we're given the x, so we're trying to solve for y. So all that you would do is in your y equals, hopefully you can see this and the glare is not too bad, I would type that regression line in here. Okay, so I would type negative 0.370x plus 962.041. Okay, so type that into your y equals. Then go table set to the second window. So I would go to my second window table set. Make my independent band ask, which mine is. Then go to table, second graph. So over here, go to table. And then I can type in any value I want here. I don't know, I wanted to try and clear, oh, I guess I just delete that. Okay, I'm going to delete the ones I had. And now I'm going to type in the value. What was the value I wanted? I wanted 1999. And so I just type in 1999, and sure enough, it gives me 222.41. And so it gives me that value instead of just doing it. So this is actually a little quicker, especially if you have to find lots of different values. Okay, check the prediction against this one using percentage error. Now we've computed percentage error before. This was a formula we talked about. You take the absolute value of the actual value minus the predicted value over the actual value times 100. Okay, so what's our percentage error going to be? Absolute value. The actual value, let's rewrite this instead of 343.13. Let's rewrite it in seconds. So multiply that by 60, and then I have 180 plus the 43.13. So that's 223. 223.13. Okay, so that's actual, 223.13 minus what did we get as our estimate? And we'll just do 4, 1 over the actual again, 223.13, and then times that by 100. So again, if I do all this in my calculator, and percentage error is 0.32% error, which is not bad at all. That means that we have a pretty good model. Our regression line is a pretty good model for what it would actually be. Okay, I'm going to stop this video here and then we'll move on to the last part in the next video.